But in here, we've got 3 speakers on the latest topics in verification. And we're starting with Aditya Devarakonda, who is a senior manager in design verification and NXP. Aditya leads design verification for advanced power systems at NXP. Prior to this, he held several roles in digital design and digital verification of mixed-signal ICs at semiconductors, Maxim, now ADI, Dialog, now Renesas, and Freescale. Aditya holds an MSEE. Thank you.
Thank you. Good afternoon, everybody. I'll start with a question. Show of hands, how many of you here work on mixed signal designs? Okay, good. 2, 3. Okay, good. Thank you. So, today I want to discuss some aspects of leveraging AMS verification and DMS verification together for efficiency and quality in mixed signal designs. In view of the diverse audience here, I want to start with an introduction as to what's a mixed signal IC and what verification of mixed signal ICs entails broadly, and the evolution of DV into DMS, again talking in terms of mixed signal ICs, and the need for a combined DMS and AMS strategy. And I would like to present a combined DMS and AMS flow, and what teams need to do when they try to transition from an AMS DV, traditional AMS DV flow to an AMS DMS flow. And then I'll talk a little on modeling, and then also discuss some pitfalls, and then wrap up with the conclusions. So to start with, what's mixed signal IC? So mixed signal ICs, they have both analog and digital functions together on a chip. You see that the world is analog, so any of the sensors or basically any of the functions that interact with the outer world, they're all analog. They have to have some analog component. So typically, this is kind of the very high level block diagram of a mixed signal IC, if you will. You have typically implemented using schematics, schematic-based design flow, and then you have digital functions which are implemented using the well-known RTL synthesis and APR-based flow. Then, when it comes to verification of these mixed signal ICs, there are 2 aspects. So the first is the verification of the electrical parameters and the performance, and also the transient behavior of analog circuits. And then the other aspect is the functional aspect, where we are trying to verify the functionality of the IC, both at the block as well as at the SoC or subsystem level. And in this presentation, I'll be mainly focusing on the SoC or the subsystem level functional verification. And why? Because my experience has been that majority of the use cases on a mixed signal IC, they involve interaction between the analog and the digital IC, analog and the digital parts. And so that needs a verification at the SoC or the subsystem level. And again, my experience has been is that most of the digital or SoC level bugs are found through that at the SoC level verification. And for verification at the SoC level, 2 approaches are used independently in most cases, which are analog mixed signal verification, popularly called AMS, and then digital verification, which is DV, which I guess most of the people in this room are aware of. So just an introduction on each of these methods of verification. So analog mixed signal verification, it is SoC level verification with an analog focus, where analog is typically represented using schema models that need the simulator's analog solver. and the digital is typically represented using behavioral models, which is our RTL design. And since analog is being represented using schematics, this is a more accurate verification method, which is orders of magnitude slower when you compare it with the DMS flow. And the other side is digital verification, which is again an associate level verification with digital focus. And in this case, analog is typically represented using behavioral models that do not need the simulator's analog solver, and digital is represented the same. And this is orders of magnitude faster since we are not using the analog solver of the simulator. So, and the accuracy of DV, it depends on modeling and as well as how robust the model verification flow is. So let's look at the evolution of DV when it, talking in terms of verification of mixed signal ICs. So traditionally, I would say, if you maybe go back a decade ago or sometime, digital DV on mixed signal ICs mostly started with verification only at the digital top, and there was lack of modeling on any of the analog blocks, and any of the analog response is provided by the test bench itself. And 100% of the digital, it was a 100% digital only focused verification because none of the analog was modeled. Basically with that, all the chip level connectivity and the functional coverage were dependent on AMS verification. And from there, one improvement was using digital top verification along with functionally equivalent models, where there is some kind of modeling for the analog, but still there is no one-to-one correspondence between the analog schematics and the models that we were using. The models were only functionally equivalent, not necessarily pin-to-pin equivalent. So that way, it was still a digital focused verification because we were still verifying only at the digital top level, but it could result in a more accurate digital verification, but still chip level connectivity and functional coverage were still dependent on AMS. The next improvement on that is using a digital top along with accurate analog real number models, and also models that are pin accurate to the actual analog schematics, so that the netlist that is used or the DUT that's used for the verification is actually generated from the chip level schematics. So this I would say is a true chip level DMS verification, where we have the actual netlist generated from the schematic, and also we're trying to use real number models that represent the analog more accurately. And again, with more accurate and fast analog behavioral models that are developed using WReal or system Verilog real number or user defined nets like ENet. When we combine this with a robust model verification, we can actually provide a reliable SOC level connectivity as well as functional coverage. So having described what DMS is, I want to present a case for why we need a combined AMS and DMS verification flow. So one thing is that both AMS, which uses more analog schematics and still doing verification at the chip level, both AMS and DMS, they both have the same goal. Basically, we are trying to solve the same problem, which is trying to prove that the IC is functional at the chip level. And with more accurate modeling, with techniques like real number modeling and as well as WReal models, the use cases and scenarios that were previously verified using only AMS, we could actually verify those now using DMS without actually using the analog solver. And then with that comes the convenience and the advantage that we could use concepts like randomization and then coverage, etc. All of them, those could be realized at the chip level, leading to a more thorough verification, a thorough SOC level verification. And one thing that's worth mentioning here is that though DMSV could provide a greater share of functional coverage because of these the more accurate modeling and everything, still there will be some use cases that would still need AMS. Some critical functions we would actually need that we verify using the actual analog schematics. So DMS cannot 100% replace AMS, but there is still some relevance to AMS. So the basic point here is that AMS and DMS working independently, working in silos without collaboration is very inefficient, as well as it is unnecessarily redundant. That's why a combined strategy which leverages the strengths of both AMS and DMS will reduce the cycle times, at the same time ensuring verification quality. So how do we develop? So how do we use a combined AMS and DMS flow? So one of the major goals of this flow is to move away from the heavy dependence on AMS verification at the SoC or chip level. The idea is to move as much coverage as possible from AMS towards the DMS side. And then, so basically we want to employ a balanced approach that utilizes both AMS and DMS. And how do we do that? In my view, that effort starts right from the verification planning. So instead of working on separate and independent verification plans, AMS and DMS should plan on executing a common chip level functional verification plan. And in the verification plan, we could clearly identify which method is to be used to cover each feature or each use case, as in is it DMS or AMS or sometimes both. And how do we classify, as in a feature or a use case, the classification, whether it has to be covered by AMS or whether it has to be covered by DMS, depends on the following factors. Those are the criticality of the feature. In this case, we need input from product definers as well as analog designers, and maturity of the analog IP and the analog models. And we talk about this more later, and the existence of a robust analog model versus schematic verification flow. We also talk about this more later. And there are also other factors like the analog and digital design approaches, as well as basically the experience of the teams on working on an AMS and DMS combined flow. So all these factors are not really an exhaustive list. They actually affect what approach we take and how do we classify each feature to be verified either by AMS or DMS or both. And another important thing is that both the AMS and the DMS leads, they have to be very clear on the limitations and the strengths of each flow in verifying each feature, so that they actually know that whether their approach is going to provide the required functional coverage and the required checking that's needed on each use case and each feature. Okay, so here this figure is from Cadence, where they try to compare the accuracy and the simulation performance or the simulation speed trade-off between the different modeling methods. Basically, for those who are very new to mixed signal, when I say simulation using a schematic, it uses SPICE models, and DMSV uses real number models, which is this bubble. So you can see that DMSV using real number models is good on the simulation performance, whereas it is much less accurate than SPICE models, which is what AMS uses. So the idea is that the verification strategy should aim at extracting maximum coverage using real number models while maintaining the required accuracy. Then how do we do that? How we do that is we, as teams, invest more in developing accurate and more sophisticated analog models. My experience has been is that this bubble could be pushed upwards, if not up to match with SPICE, but at least to an adequate level, such that DMS can actually provide a lot of coverage on the chip and reduce the dependence on AMS verification. And there are some other factors that need to be taken into account as teams try to transition from an AMS DV approach towards an AMS DMS flow approach. And to do that, we need alignment from other disciplines, as in alignment from analog design, digital design, and basically the verification teams as well as the modeling teams. And a very important thing is for the design teams to adopt a more top-down design approach. Why? Because by following a chip level DMS verification, we have actually increased the scope of DV. So so the chip architecture and the top level pins, as well as block ports, and as well as the analog to digital interactions, they have to be very clearly defined. Otherwise, and also a well-defined partitioning of analog and digital blocks at the chip and the sub-block level is needed. And also a desirable feature is to have a common test bench for both AMS and DMS. We do have, we had state-of-the-art tools available for some time, which allow us to do that, where we can actually select which type of model we want to use for a particular simulation, thereby whether we decide and the analog solver is invoked or not. And apart from that, the analog modeling as well as model verification is needed, because the integrity and the reliability of the DMS verification, it actually depends on the availability of accurate and well-written analog models. And these analog models, they should be thoroughly verified against the schematics. And a model versus schematic regression should be set up, and it should be run periodically as well as whenever the design changes. So here I try to present like a flow that could be used for a robust analog versus model versus schematic verification. So generally, analog models, they are created either from the analog architecture requirements or from schematics as well, if the schematics are available. And then once the models are created, those models have to be verified against the schematic for functionality. And then the regression should be run periodically, and if there's any failure, basically the analog model or the schematic needs to be updated, and the process is repeated throughout the verification phase of the chip. And then with a top-down approach, analog models could also facilitate an early proof of concept for the chip architecture, because currently without analog modeling, basically we have to wait for the full schematic design to be complete before actually proving that the architecture works. And another thing that could be done is, generally when analog IPs are developed, instead of just developing just the schematic, the IP could be extended to also include analog models, so that analog model is readily available for each analog IP. So here I show some pitfalls that I have seen like through my career following this approach. One case is an AMSV heavy approach, which you would see typically in many mixed signal groups, where a lot of coverage is being provided by AMS because of using very simple analog models. And basically, that means that AMS becomes a bottleneck for tape-out because of the really long simulation times. The other approach is a DMSV heavy approach with very complex analog models. And in that case, if even the very minute features are implemented in models, it means that we will see a lot of model failures in our regression. And the other case is a lack of a strong top-down design flow. So to conclude, basically I try to present a combined approach for SOC level functional verification. Adopting a well-balanced AMS and DMS verification flow is expected to reduce the total time and resources spent on verification. And then having a robust analog model creation and verification flow will ensure that the reliability and the coverage achieved through DMS. And here basically I try to show that if the mixed signal verification is the puzzle, then basically these are 4 of the major pieces that solve the puzzle, which are DMS, AMS, and analog modeling and model verification, and as well as chip level net listing from schematic. Thank you.
Thank you. Unfortunately, I don't think we've got time for questions, so because we want to move on. I think people want to finish on time, so thank you very much.